In this video, we'll be looking at how we can use a power series to solve differential equations, particularly how we can solve differential equations with non-constant coefficients. Indeed, here we have a second-order differential equation. But in my previous videos, we looked at how we can solve these types of differential equations, where the coefficients here of double prime and y are constants. Conversely, in this example, we have functions of x instead of constants. And whenever we have to deal with these types of differential equations, it's always good to look at the power series solution. So what we do is we write our solution y of x as an infinite series. So n going from 0 to infinity of a coefficient c of n times x minus x naught to the power of n. But what does x naught represent? If you're familiar with the concept of a Taylor series of a function, well, you know that we can approximate a function that satisfies certain conditions with a power series similar to this, where we approximate this function around a point x naught. Okay, and here it's a similar concept. Instead, we're not talking about approximations. Here, we're writing a function in another way, but centered at a specific point, x naught. It's instrumental to note that this differential equation needs to satisfy certain conditions in order to be able to write our solution in this power series form. And to see what these conditions are, what we first need to do is write our differential equation in standard form. So here we're supposed to have 1 as a coefficient for the second derivative. And we do that by dividing by 1 plus x squared. And so this is the standard form of our differential equation. Indeed, we have a differential equation in the form y prime prime plus a function p of x times y prime plus another function of x, q of x, times y is equal to 0. And the requirement for using a power series solution is that p of x and q of x need to be analytic at the point x naught. What does it mean for a function to be analytic? Well, it means that we can write p of x and q of x as a power series, just like y of x. And these power series need to converge. But obviously, writing the power series of these two functions in this case can be quite tedious. And so what we do is we simplify our assumptions by saying that if our function looks nice enough, we can consider it to be analytic. So this is not rigorous, but usually we will deal with relatively nice differential equations. In later videos, I'll be explaining in detail the analyticity of functions. But now we'll focus on how to use a power series to solve differential equations. And remember that we talk about analyticity of a function at a specific point. So here, for example, p of x and q of x are analytic about the point x equal to 0. So x equal to 0 is called an ordinary point because these two functions are analytic about that point. And therefore, we can write our solution as y of x is equal to the infinite series of n going from 0 to infinity of Cn times x minus 0, and therefore just Cn times x to the power of n. Now that we've talked about the requirements for using a power series solution, we can solve this differential equation. But one crucial point I want to make is that to use this power series method, it is often better to use the original form of this differential equation rather than the standard form. And why is that? Because here we can see that our coefficients are fractions. We have x over 1 plus x squared. And so when using the power series, it is often quite difficult to deal with these denominators. And so what we do is we use the standard form, which is much nicer because our factors are quite simple. Now, what I've done here is I substituted the expressions for y and its derivatives, these expressions that we derived in the previous video on the power series solution, and I've plugged them into our differential equation, which yields this equation over here. Now what we need to do is we need to absorb these factors into each summation. So for example, in our first term, we distribute the 1 plus x squared. So 1 times our sum is the sum itself. So n going from 2 to infinity of Cn n minus 1 x n minus 2 plus x squared times our sum. And x squared, we can multiply with the x to the power of n minus 2. And so we get x times to the power of n minus 2 plus 2, which is x to the n. So we have the infinite sum. Then going from 2 to infinity of Cn n minus 1 x to the power of n. And we reiterate this process for this factor over here, where we distribute the 4x. And so x times x to the power of n minus 1 is just x to the power of n. Now what we need to do is we need to algebraically manipulate our expression in order for each sum to have an expression containing x to the power of n. So the problem with this term, for example, is that x is raised to the power of n minus 2. But we want it to be raised to the power of n. And the reason we want to do that is because if every sum has the same exponent for x, well, it's easier to determine the coefficients c of n. Now, I'm going to give a quick elementary example to see why that is the case. Let's say we have an equation with one polynomial on each side, and we want to determine the coefficients a, b, and c, as well as m, n, and p. And the way we do that is if we have an equality between two polynomials, the coefficients of x squared for both polynomials will be equal to each other. So for example, in this case, a will be equal to m. And the same applies for the coefficient of x. In this case, b is equal to n. And similarly here, we have c times x to the power of 0, which is 1, and p times x to the power of 0. And so these two coefficients need to be equal to each other. And so this is what happens when we have an equality between two polynomials. And so in this case, if we can regroup our sums into one bigger sum, where n goes from 0 to infinity, and we have a coefficient which I will call an, times x to the power of n, well, that will be equal to 0. But I can rewrite 0 as being 0 times x to the power of n. And if we match coefficients, we can see that an has to be equal to 0. And that's why we want to regroup our sums in terms of x to the power of n. So what we need to do is, in this case, we need to transform x to the power of n minus 2 into x to the power of n. And the way we do that is by shifting the index of our summation. And so you may have been taught to change variables whenever we shift indices. But I want to teach you a nice technique in order to be a lot quicker. In essence, the sum is composed of two parts. First, we have the index in our summation. So n starts from 2 all the way to infinity. But then we also have the index that is within the sum. So c of n and n times n minus 1 times x to the power of n minus 2. And one important property is that when we increase the index that is within the sum by a certain amount, we need to decrease the index that is in the summation by that same amount. So if we increase n by 2, well, we need to decrease n by 2 in the summation. And so, for example, our goal is to have x to the power of n, and therefore we increase n that is within the sum by 2, and therefore we get cn plus 2 times n plus 2 times n plus 1 times x to the power of n. But when it comes to the summation, since we increased n by 2 here, we need to decrease n by 2 in the summation. So now n starts from 0 and not 2 because n minus 2 is equal to 0. And infinity minus 2 is always infinity, so this will remain infinity. So we have the same exponent for x, but now in order to regroup our sums, our four sums, into one bigger sum, we need the indices to be equal to each other. So now we need n to start from 0 for these two sums. And the thing is, if we change the index from 2 to 0 in this case, well, it won't change our sum. Indeed, if n starts from 0, well, we would have Cn times n minus 1. But since n is equal to 0, the first term cancels out. And similarly, if we have n is equal to 1, well, n times n minus 1, well, n minus 1 is 0. So the first term also cancels out. So if instead of starting from 2, we start from 0, the sum doesn't change. The value of the sum doesn't change, because the first two terms will be 0. And similarly for here, if n starts from 0, well, we would have n, so 0 times x to the power of n. And so the first term is also 0. And therefore, we change the index to 0 for each summation. And now we can regroup our four sums into one bigger sum, where the common factor is x to the power of n. And so we have a big sum starting from n equal to 0 all the way to infinity of x to the power of n times Cn plus 2 times n plus 2 times n plus 1. And so this corresponds to our first sum over here, plus Cn times n minus 1 plus 4Cn times n plus 2Cn. And that has to be equal to 0. And what's great about regrouping all of the sums into one big sum is that now we know that this expression that I've underlined in green has to be equal to 0 in order for the equality to hold for all x. Now, before we move on, I want to do a quick recap of everything we have just seen. When we're using a power series to solve a differential equation, the main goal is to try to find an expression for c of n. And the way we do that is we substitute our power series into our differential equation. And so we get an expression containing many sums. But since we want to determine the expression of c of n, we need to regroup all of these sums into one bigger sum. And the way we do that is by, first of all, having the same powers of x in each sum. And the way we do that is by shifting the index. And then what we need to do is we make sure that the index always starts at the same point. So in this example, n has to start from 0 for each of the sums. And knowing all that, we can regroup everything into one big sum. And this will allow us to obtain an expression for c of n. We don't get a direct relationship, but we get a recurrence relation for c of n, which allows us to determine what kind of power series we have to solve the differential equation. Back to our exercise, we can factorize by c of n over here. And we note that we have n times n minus 1, which is n squared minus n, plus 4n. So we have n squared plus 3n plus 2 over here. And that's just equal to Cn times n plus 2 times n plus 1. And therefore, since this whole expression has to be equal to 0, we get that n plus 2 times n plus 1 times Cn plus 2 is equal to negative Cn n plus 2 times n plus 1. And so these factors cancel out, and we get Cn plus 2 is equal to negative Cn. And one important thing to note is that whenever we have a recurrence relation relating n plus 2 to n, this means that we get two parts in our general solution, the odd terms and the even terms. because, for example, C2 will be equal to negative C0. And similarly, C3 will be equal to negative C1. But we can't get a specific value for C0 and C1. And so our general solution will contain these two arbitrary constants, which makes sense because here we have a second order differential equation, so we need two arbitrary constants. And for example, we can't write C1 in terms of C0 because they're not related. Only the terms with the same parity are related through this recurrence relation. And so now we have our expression for our power series solution, which we know initially it was C0 plus C1 times x plus C2 times x squared plus C3 times x cubed, etc. Well, C0 and C1 are arbitrary constants, but we can express C2, C3, and the subsequent terms in terms of our arbitrary constants. And so we have C0 plus C1x, and C2 we know is equal to negative C0. So negative C0 x squared minus C1 x cubed. And so what we do is we factor the C0s and the C1s. And so we get C0 1 minus x squared plus etc. plus C1 times x minus x cubed, and so on. But before we declare that this is indeed the solution to a differential equation, we need to make sure that y of x indeed converges, because it wouldn't make sense to have a solution that blows up all the way to infinity. And to make sure that the solution converges, we need to use the ratio test. And what's important to note is that y of x is actually written in terms of two infinite series. So the first one, which I will call y1 of x, and the second one, y2 of x. And so we need to make sure that each of these series converges using the ratio test. So we don't use the ratio test for y of x as a whole, but rather for each part of the solution. Indeed, if each of these series converges, then y of x as a whole converges. And therefore, using the ratio test, we get that r, which is the limit of, well, the successive terms in each of our series. So Cn plus 2 times x to the power of n plus 2 divided by Cn times x to the power of n, absolute value, of, well, the limit as n tends towards infinity, of course, of this ratio is equal to the limit as n tends towards infinity of, remember, Cn plus 2 is actually equal to negative Cn. So negative Cn divided by Cn is negative 1, but since we have the absolute value, it will just be 1. So we have the absolute value of x squared. And one thing you may wonder is, if we're taking the ratio of the successive terms, why don't we have Cn plus 1 instead of Cn plus 2? Well, the reason for that is because, remember, we're taking the ratio test for each part of our solution. And so here, the two successive terms have a difference of exponents, which is 2. So here 1 is 1 times x to the power of 0, and the subsequent term is x squared. And likewise for y2. And so essentially, we've divided our initial power series into two different power series. And in order for these series to converge, well, the ratio has to be less than 1. And therefore, we get a radius of convergence, which is equal to 1. And note that this ratio actually applies for both of these series. And why is that the case? Well, because the recurrence relation covers both of these series. And therefore, this recurrence relation is the same, whether we apply it for y1 or y2. And therefore, the ratio will always be the same, whether we apply it for y1 or y2. One final thing before I end this video is that it's always worth writing these series in a closed form. In other words, instead of having suspension points over here, we write these series as one single expression. And so how can we do that? We can actually use a Taylor series to write these two series in a closed form. Remember that 1 over 1 minus x? Well, that can be written in terms of a geometric series. So 1 plus x squared, etc. And so now if we substitute minus x by x squared, we get 1 over 1 minus x squared is equal to 1 minus x squared plus minus x squared to the power of 2, etc., which is just 1 minus x squared plus x to the power of 4, etc., which is exactly this series we have over here. So actually, what we notice is that y1 of x is actually equal to 1 over 1 plus x squared. And I will leave it as an exercise for you to show that y2 of x is equal to x plus 1 plus, divided by 1 plus x squared. And you can use the binomial series to prove that this expression is equal to this. This was quite a long video, but it was definitely worth it because it taught us how to use a power series to solve differential equations with variable coefficients.